as possible. But I don't think I managed at all stages. So if there are technical questions on the way, please go ahead. And then you can also notice that I have a slight change in the title. So when I announced the seminar, I had question marks, and now they move to exclamation marks. And I hope that it will be clear what the difference is during the talk. So let's get started. So this is the outline. So I will have a brief introduction. And then there are three main parts of the talk. So I will discuss stability coefficients computed from the Wetterich equation, stability coefficients computed from the composite operator equation. I will compare the two approaches in the computation, and then I will have some conclusions, and I hope we can have some discussion on the conclusions afterwards. So since this is a seminar on asymptotic safety, let's recap quickly in the introduction what we want to do. So we have a non-Gaussian randomization group fixed point, and this fixed point is supposed to provide the high energy completion of the gravitational interactions. In the best of all cases, this will ensure that there are no unphysical UV divergences. In a second step, we want the fixed point to be predictive, and the predictive power is encoded in the stability matrix. So in the end, we want to have only a finite number of UV attractive eigendirections for this fixed point, and this will give us predictivity. So once we have point 1 and 2 into place, we can move further on and connect the fixed point to the effective dynamics. And on this basis, we will be able to connect two observations, either by general relativity or by the standard model of particle physics, if we supplement the construction by additional meta degrees of freedom. In the end, we also want to have some structural demands on the construction. So we would be happy to see that it can remove space-time singularities, that it is causal or compatible with microcausality, it's compatible with positivity bounds. You can add many more structural demands in here. What I am going to do in this talk, I will focus on part 2, namely predictive power of our fixed point. And then let me also introduce my 3 little helpers in the talk. So there will be a yes, there will be a no, and also a maybe. And you can check at which stages of the talk they will appear to get the main message. So let's first make a brief introduction to predictive power. So suppose we have computed beta functions somehow. So this tells us how dimensionless couplings Ui change with respect to our randomization group scale T. By definition, a randomization group point or fixed point is a point where the beta functions here vanish simultaneously. So we have beta I is equal to 0 for all these functions. Then we can study the RG flow in the vicinity of this fixed point. For that purpose, we linearize the flow at this specific point. The 0th order term in the expansion vanishes. And then the first leading term contains the stability matrix B. So by definition, that's the derivative of the beta functions with respect to the coupling, evaluated at the fixed point. And you can see this expression here as the first order in a Taylor expansion. So important, please store the concept of the stability matrix in your short-term memory. So that will be the key instrument in this talk, and all the discussion will essentially evolve around this object Bij introduced on this slide. So what is important is that the spectral properties of this matrix essentially tell us about the predictive power of the fixed point. How can we see that? So we have the linearized flow here. This is a linear differential equation. And we have the tools to actually solve them. So we have the matrix Bij. We compute its eigenvalues lambda and its right eigenvectors Vi. So by definition, we have B times V is equal to lambda times V. And then we can construct the solution of the equation that we have up here. So clearly, it knows about the fixed point, U star, and then there are deformations encoded in the C here. And in these equations, we can discriminate two cases, depending on what the real part of the eigenvalue lambda is. So if this real part is smaller than 0, then you can check if you send k goes to infinity on this one, this corresponding term in the sum will vanish by itself. So the corresponding Cj is a free coefficient. Conversely, if the real part lambda is larger than 0, then this will not approach the fixed point along this direction. And in order to do so, we have to set the corresponding coefficient Cj to 0 in order to have the fixed point providing the UV completion of our flow. So for each lambda I, with real part lambda I is smaller than 0, there's exactly one free parameter in the construction. Now here's the cartoon version of what I've discussed. So we have a theory space which contains all our interactions. Somewhere in the theory space, there's our fixed point of interest. And this fixed point divides the space into two subspaces. The one that is relevant for us is the UV critical surface. So these are all the RG trajectories that end at this fixed point when we send k to infinity. Asymptotic safety then states that the physics that we are looking for is encoded in precisely this surface. And then you see that we have a set of free parameters equaling the dimensions of the surface. Then there has been some recent progress on actually constructing the surface here on partial differential equations. So Agustin managed to recast this in terms of linear PDEs, which makes the construction of the surface very efficient. But for today's talk, we are only interested in an infinitesimal environment around the fixed point. So we want to have a tool to compute the stability matrix. Tool number one, we can do it using Wetterich's equation. How will this proceed? So we have Wetterich's equation for gravity. On the left-hand side, we have the randomization group time derivative of the effective average action. On the right-hand side, we have to evaluate a trace. This contains the regularized propagator of the theory and the time derivative of the regulator. Now, we have this formally exact equation. We can use it to compute beta functions. So we make an ansatz for the effective average action, typically containing only a subset of all possible interaction monomials. This is done here. In this way, we introduce scale-dependent couplings. So these are the UIs given here. We substitute it into the Wetterich equation. Then we read off monomials on the left and the right-hand side, and the coefficients of these monomials give us the beta functions. Now, there are several classes of approximations that one can consider at this stage. So first, one can work at the background level. So that means the left-hand side of the flow equations is evaluated at 0th order of the fluctuation field. Or you can systematically expand the effective average action around a fixed background, powers of the fluctuations, both of them valid approximation schemes. Also, you can play with the dimensionality of the projection space. So most often one has finite dimensional approximations where the number of operators contained are actually finite, but this is not a fundamental limitation to the program. So we can also look for infinite dimensional approximations where we really exploit the full functional power of the RG equation. For the purpose of the talk, I will limit myself to discuss background level flows. So everything is evaluated at fluctuation field is equal to 0. Then we can ask ourselves, how can we organize the effective average action in such an approximation? And it's convenient to actually do this by power counting. So at lowest level, we get the cosmological constant. Then at 2 derivative level, there will be the Ricci scalar. At 4 derivative level, we get 3 interaction monomials that can be constructed from the gravitational field. So there's R squared, there is the Weil tensor squared, and there's the Ricci tensor squared. And by adding more and more derivatives, we get more and more terms. For the purpose of the talk, we focus on f of r type truncations. So we work along this ray. So we will only consider powers of the Ricci scalar in our ansatz for gamma. Now there has been significant work in this direction. So let me highlight 3 different categories in which you can group the results. So polynomial f of r projections. So here we use an f of r that is actually a finite polynomial. Then we have a class of functional f of r projections. So here we want to learn about the structure of the full functions. And then also relevant for the talk are f of r type projections using composite operators. So I highlighted also some literature that is relevant for this particular talk in green. And if I missed 1 or 2 of the works, I tried to be systematic, but this is possible because there was really a bulk of research going on in this direction. So my apology if there's something missing. So what do we do if we want to have a polynomial f of r truncation? So we take the effective average action, and then the starting point is a function which depends on our RG scale k and is a function of the Ricci scale. In order to make this well defined, we have to add gauge fixing and ghost terms. So they will appear here in the dots. For the purpose of the talk, this will be technical details. So let's leave them out and not focus what happens here. Now we can substitute this ansatz into Wetterich's equation. We can evaluate the trace on a spherical symmetric background. And in this way, we get the partial differential equation for the function fk of r. We can take this partial differential equation, we can expand it at r equals to 0 up to very large orders in r. And this gives us a finite dimensional set of beta functions for the corresponding couplings in this ansatz. So in practice, that might look as follows. So the top line gives us the ansatz. We expand in a polynomial in R with maximal degree n scalar. The UN are made in such a way that they are dimensionless. We can compute the beta functions according to the scheme that we had on the previous slide. And then we can check for fixed points. And the position of the fixed point is given here when you vary n scaling. So you can go from 1 up to 6. You see that there's rapid convergence in the position of the fixed point. Since you have the beta functions, you can also go to the stability properties, the stability matrix close to this fixed point. You can systematically compute the corresponding eigenvalues. And in this way, you quickly find that the eigenvalues converge rather rapidly. And there are only 3 eigenvalues with a negative real part. So these are associated with relevant directions. And once you add new directions in this polynomial, you see that all the new eigenvalues come with positive real part, and their size actually increases. So the absolute value becomes larger and larger. So when you add new directions here, this does not open up any new directions. Now here we went up to n equals to 6. People have gone much further than n equals to 6. So we have results up to Rn to the order 70. Here this plot to the left shows the 3 relevant eigendirections. And then in this strip here, you see all the irrelevant directions that can be approached along this line. So important, the property holds. And what is also important is that essentially the eigenvalues that you have for the stability matrix are closely linked to the classical mass dimension of the corresponding operator. So everything follows essentially linearly in this line. So this is super nice because it tells us, okay, predictive power is great. Yes, we have it. Now we can go further and we can have a second way of computing the stability matrix. We can use composite operators in order to do so. So what's the idea behind that? So in principle, we start again with the effective average action, but we do an extension of the standard effective average action. So this is the object that is extended. This is the standard part. And then we add additional operators to the construction, which are typically not included in gamma. So what you could think about in terms of the O tildes are non-local operators, for example, associated with geodesic distances or similar geometric objects. Now, you can substitute such an ansatz. In Wetterich's equation, you can expand in the sources En. And in this way, you get an equation that tells you about the k-dependence of this operator's O tilde. So the corresponding equation is given here. And this is the composite operator equation. It looks slightly more complicated than Wetterich's equation, but structurally, we have essentially, again, a one-loop structure. So we start with a propagator. We have the insertion of the second derivative of the composite operator. We connect it again to a propagator, and then we close the loop by our regulator. However, this construction needs input from the standard part of the effective average action. So in order to evaluate this equation, we need input on the propagators and also, if we are interested in that, about positions of a fixed point U star. So this has to be fed into this formalism from external knowledge. Now we can use this equation to actually compute a stability matrix. So nobody can forbid us to tell us that the O tilde in our extensions are actually basis vectors spanning our theory space. So we take the set of O tildes to be the O's that we worked in initially. We multiply them by a k-dependent coupling constant or coupling matrix Z. And we can also introduce the canonical mass dimensions of the operators On as minus Dn. Then we can start from the set bar and compute a dimensionless anomalous dimension matrix, gamma, from this. So essentially, this is the dt derivative of log Z, dressed up with proper factors of k to make this dimensionless. And we can use this anomalous dimension matrix to build up the stability matrix based on composite operator equations. So this will have a classical part. So this knows about the dimensionality of the operator. And then there's a quantum part, the gamma, which knows about the anomalous scaling dimension sitting here. Again, in order to evaluate the B that sits here explicitly, we need knowledge about the couplings of gamma. And this has to come from Wetterich's equation. Now we want to use this to do an f of r type computation. So what do? We take gamma and we expand this in powers of r, take this to be a polynomial in powers of r up to order n proper. Then we can also take our composite operators. We also take them in the form of powers of the Ricci scalar. The idea is that in this way, we can go take the n scalar much larger than n propagator and still get information about the scaling of operators R with a very high exponent n here. Now we can do this. First, we can take the propagator to be n equals to 1. So these are the propagators that you get from the Einstein-Hilbert action. And you can work in an approximation where you only retain one of these O tildes and take this to be the operator at order R to the n. Then you can compute the corresponding eigenvalue of the stability matrix. This is a constant shift. Then it knows about the classical scaling dimension of the operator. And then there's a quantum correction coming on top of this. And if you substitute dn and n explicitly, you find that this expression is negative for all values of n. Good. This is as it is. So based on this approximation, you would say that, wow, all my eigenvalues are suddenly UV attractive. So that could be a problem with predictive power. Of course, the single operator approximation is rather cute, and you can study the full dimensionality of this matrix Z bar in here, also taking the off-diagonal elements of this matrix into account. Also, this has been done. And here is the result for the spectral properties of the stability matrix using the propagators of the Einstein-Hilbert action and a scaling dimension of 25, 50, and 100. So 100 is the blue line, 50 is the orange line, scaling, and the green line is 25. What is remarkable about this plot is that the curves shift to the right. So in principle, it tells you, when you increase n scaling, you add new eigenvalues, eigendirections, and the eigenvalues appear with either sign, either positive or negative. So while our problem has slightly improved in the sense that we also get irrelevant directions now, we still get an infinite number of relevant terms from this construction. So again, there is a problem with the predictive power, and these results turn out to be robust also when we increase the size of the propagator beyond 2. So essentially you end up with the same curves. So that brings me to the summary of part 2. So what do we say about predictive power from this type of computations? The clear answer is no. There's a finite, infinite number of relevant parameters that we have to determine. So clearly there is some tension now. So fair question, what is going on? So let's look into the details between and compare the two constructions. So what do we have on the table? So if we do an f of r type computation based on Wetterich equation, we have a finite number of relevant parameters. If we do a similar computation based on composite operators, we have an infinite number of relevant parameters. So in order to understand this, we have to understand more details about the structure of the stability matrix. So typically our B star evaluated on the fixed point has two parts. There's a classical part. This is given by the classical mass dimension of our coupling. And there are quantum corrections sitting on top of it. If you look at the structure from the perspective of the Wetterich equation and the composite operators, the classical part is identical. So no difference here. It is all in the quantum part where the two formulations actually differ. Now, could the almost Gaussian scaling that we saw from the Wetterich equation actually be associated with the quantum part that we have here? So it's the comparison that we have here suggests that this might be the correct way to think about it. So let's follow up on this. So when we construct a regulator in the Wetterich equation, this part typically consists of two parts. So there is a wave function part, which I call calligraphic Z. This depends on the coupling constants U. And then there is a profile functions Rk, which carries the dependence on the loop momentum. That means if we construct the t derivative of this, we actually get two contributions. The dt can act on the z, and it can act on Rk. Now we can separate these two contributions and write the Wetterich equation essentially in left-hand side equals right-hand side form. So the green part is what is produced on the left-hand side. The right part is what happens on the right side. So this is what the trace gives us. And I separated out two structural parts. So there is omega. This is the functional trace proportional to dt Rk. And then there's the omega tilde. This contains the contributions of the functional trace, where the dt derivative here acts on the prefactor z. So essentially by chain rule, you get the dz by du, and then du dt, and this is what is written in here. Now we can solve this equation for dtu to get the beta functions. This is written here. So there's a classical part, and then there's a matrix 1 minus w tilde inverse multiplying omega. Good. So this is the structural form here. We can rewrite the construction slightly and bring it to the level of the stability matrix. So we recall that the stability matrix is the derivative of beta with respect to u evaluated at a fixed point. By doing some formal manipulations, we can rewrite the stability matrix in the following form. So there is a global inverse matrix multiplying this matrix here. The D is the classical dimension piece. The gamma here is the contribution that would be the composite operator equation. And the gamma tilde collects all the extra terms that appear in a computation from Wetterich's equation. So essentially, this split into composite operators and Wetterich equation drives the definition of the gamma and gamma tilde that we have used here. So we want to make the difference between the two formalisms as explicit as possible. And then we can check what the composite operator actually does. It sets the omega tilde here to 0 and it also sets the gamma tilde in here to 0. So in this way, we have a formulation in which two formalisms fit onto one line. Now we can ask about the structure of the matrices that come in here. Specifically, we can go back to the f of r projections and we compute the entries of the building blocks. So on the left-hand side, we have the matrix entries of classical dimension plus gamma. This is the typical composite operator contribution to the equation. And what you see here, so n and m are the matrix indices that we have here. Low-dimensional truncations would be in this corner of the plot. And the entries of these matrices actually grow in size, and they grow exponentially in size when we increase the size of the matrix. So if we make the matrix one step bigger, it's the new terms that actually dominate. The same is true for the matrix that we have multiplying the gammas. Also here we observe that the entries themselves grow exponentially and the large values appear at large index numbers. So takeaway message, each of the building blocks has exponentially large entries, and the largest entries are found at the points where we add new directions. Now we can take these two building blocks together and construct the matrix B, stability matrix. And then we observe that essentially exponential growth between numerator and denominator is gone. So this has two consequences. The inverse matrix of gamma tilde wipes out the information that we have about this classical scaling dimensions. And the almost Gaussian scaling that we see is for certain associated with the quantum contributions gamma, gamma tilde, and omega tilde. Now we can dig into the details. So what actually creates these exponentially large entries in the computation? And after some trial and error, we were able to actually identify what's going on. So we can look at the two-point function in the conformal sector. So this is the matrix element gamma 2 plus rk associated with the trace of the fluctuations. So when we evaluate this at the fixed point, we get a polynomial of order 8 with fixed coefficients. And we can look at the root structure of this polynomial. So here we systematically increased the order of this polynomial. But what happens if you go beyond 5? There's one very stable root close to the origin. So this is situated here, and it converges to minus 0.13. And it is this root that actually dominates the entire computation. So all the quantum contributions for large values of n scalar are linked to this specific root in the two-point function. That means you can now make very crude approximations. So you can evaluate only the flow equation using the conformal contributions only, and a very low order of the heat kernel. It will be reliable in the sense that it captures all the essence of the computation. So in essence, what this root does is it leads to exponentially large coefficients when you expand close to the position of this root. Now, we can also ask at which order such effects become dominant. So by directly comparing the eigenvalues that you get from the composite operator and the functional randomization group, and then you see that for low orders, you essentially get a picture that coincides. If you go to higher orders, say order 4 and 6, there are first deviations sneaking in, and the difference between the two formalisms grows, essentially when you increase the number and scaling, so the order of the operator that you use in the expansion. Now, what do we learn from this comparison? So first, we learned that when we probe the stability matrix at the Reuter fixed point, it is dominated by quantum contributions. So yes, the almost-Gaussian scaling has a quantum origin. Secondly, the stability matrix is dominated by the conformal factor. So essentially, it's the root closest to the expansion point that rules all the results. At third, we observe that the regulator generates terms dtu. So these are associated with this matrix W tilde. And this contribution is present in the Wetterich equation, and it compensates the large entries in gamma and gamma tilde. In the composite operator, this cancellation mechanism is absent, and then you are left with the large eigenvalues of gamma at the quantum level, and essentially this gives all the problems that we have seen with the stability matrix. And this brings the danger, so the almost Gaussian scaling that we have in these f of r computations could actually be a very regulator-dependent statement. So for one regularization mechanism, it is there, for the other it's not, and this is worrisome. Okay, so this makes the appearance of the last of my little helpers. So based on this conclusion, I would say predictive power, maybe. And we understand what needs to be understood in order to make this maybe a yes or no. So what did we learn in this talk? So if we work at the level of f of r approximations and work with low values of the polynomials, then the two formalisms essentially agree. They disagree if the polynomials start to have large orders, where large is at order 6 or 8. So then one computation gives stability coefficients that essentially behaves classically. The other computation gives stability coefficients that are not bounded in on one side. And we also have the insight that this feature is actually triggered by the analytic structure of gamma 2 in the conformal sector. So now, what to do? First, one should see this as a positive development. So there's tension in the room, and when there's tension, there's something to be understood. And if we can flag down what we should understand better, that will lead to progress. So in principle, this is a very good thing. There are some options based on these insights that we could try to understand better. So we can make an effort of a better understanding of our propagators, especially in a curved background. And we can try to focus on progress on the functional frontier. So the questions in the room is the f of r expansion similar to the local potential approximation that we have for the Wilson-Fisher fixed point? Or in other words, is the Reuter fixed point really curvature dominated? Of course, these are my personal viewpoints of what to explore in these directions. And at this point, I would also appreciate to have some discussion if there are more ideas and insights on this matter. So thank you for the attention.
All right. Thank you very much, Brian, for the nice talk.